Okay guys, we're going to continue on with chapter 9. In this lesson we're going to talk about solvation. Solvation is a fancy way of saying that we're going to dissolve something. Okay, so I hope that you have your chapter 9 guided notes out and are following along here. In the notes you're supposed to write down the definition for solvation. It is the process of surrounding a solute particle with solvent particles to form a solution. So basically, solvation is to dissolve a solute. We're trying to dissolve it. Remember, just a review from last lesson, a solution is made up of two parts. There's a solute and a solvent. The solute is the solid part that gets dissolved. The solvent is the liquid part. Usually, the solvent is water. Okay, so solvation is just this process of dissolving the solute in the solvent. Solvation in water is called hydration. So if you're dissolving something in water, we're hydrating it. How come solvation happens? Well, the attraction between dipoles of a water molecule and the ions of a crystal are greater than the attraction among the ions in the crystal. And so the solute, the water, the solvent, the water is able to rip apart the solute and dissolve it. Okay, so I've got a slide here that kind of shows that. If we have some sodium chloride, this is the solid part. We're going to put it in this water. So this is the solute. Okay, it's the solid part that gets dissolved. We're going to put it inside this water. And what happens is the water molecules inside this beaker will rip apart the solute. And so it just tears it apart into sodium ions and chlorine ions. So they separate in the solution. So now there's two particles. There's a sodium particle and there's a chlorine particle. If we look at this in more detail, water is polar. We just got done studying water, and it looks like this, its Lewis structure does. And if we were to draw the dipole moment arrow, this side, the oxygen, is slightly negative. These hydrogens here are slightly positive. So water is a polar molecule. It will interact with the positive and negative ions of the salt. So chlorine is the negative particle, and the sodium is the positive charged particle. I want you to look at how water attacks the solute. So this big chunk right here is salt. This would be our solute. And the water is the solvent. It's going to come in here and attack it. If you look at how solvation works, to dissolve the chlorine particle, look at which side the water is surrounding this chlorine. These are the hydrogens here. The hydrogens, if you remember, are slightly positive. So the hydrogens, because they're positive, will surround the chlorine, which is negative. Remember, the opposite charges are attracted to each other. And so the hydrogens face the chlorine. Well, when it's dissolving the sodium, because it's positive, I want you to notice how water will flip around, and now the oxygen, because it's negative, is facing the positive sodium ion. And so that is what makes water such a good solvent. It can just flip around. It can either surround a negative particle with the hydrogens, or it surrounds a positive particle with the oxygen here. So notice how the oxygens are facing it, or the hydrogens are facing it. And so when something is dissolved, it is completely surrounded by water molecules. So this will take some time in order for the water to come and break apart all of the sodium and the chlorine ions. But once it does, then we would say that the salt is totally dissolved in the water. Okay, again, this just kind of shows the same process here for the chlorine, which is a minus charge, it has a -1 charge, so this is a -1. When water surrounds it, it's going to be the hydrogens here, because they are slightly positive, that are going to surround the negative particle. Down here, where the sodium has a +1 charge, it's going to be the oxygens, because they're slightly negative, that are going to surround it. Anyway, hopefully that kind of makes sense. Well, there's this principle in chemistry, especially when we're studying solutions, that like dissolves like. So like dissolves like. So let's talk about that. There's something to fill in the notes here. So in your notes, like dissolves like means that polar solutes can be dissolved by polar solvents. So in order for something to dissolve, the polar solute must be dissolved in a polar solvent. So like dissolves like. The opposite of that is true as well. Nonpolar solutes can be dissolved in nonpolar solvents. So nonpolar solutes can be dissolved in nonpolar solvents. Let me talk about this for a second. If you let's say you got some grease on the carpet. So you had grease on your shoe, and you walked in your front room in the living room, and you tracked grease in on the carpet. Would it be a good idea to wash that grease out with water? So you got a rag and you got it soaking wet, and you tried to rub it out with that water. Would that be a good idea? And hopefully you're saying no. Grease is a nonpolar solute. So a nonpolar solute would be grease. If you tried to wipe that grease out of your carpet with water, which is a polar solvent, they would not dissolve each other. I mean, you couldn't dissolve grease in water. And so all you would do by trying to rub that out of your carpet, all you would do is spread that grease into a larger stain on the carpet. So that wouldn't work. And so carpet cleaners, they would have to know this principle. It's a good idea to know what's spilled on the carpet first. If it's a polar molecule, then yeah, sure, water might be able to clean it out. But if it's a nonpolar molecule that's spilled in the carpet, you've got to find a nonpolar solvent in order to get that out of the carpet. Here's some examples, okay? So I've got some molecules here. Water is polar. CCl4, let me draw its Lewis structure. We'll look this, and so it's symmetrical left and right, it's symmetrical up and down, so this is nonpolar. I2, iodine, looks like this. It is symmetrical both left and right and up and down, so this is nonpolar. C6H12O6 is glucose, it's sugar. It is a polar molecule. This is also polar, and this molecule is polar. So I've got some questions for you. Let's see if we can answer them. First of all, will iodine, which is right here, will iodine be soluble in water? So iodine, which is nonpolar, will it be soluble in water, which is polar? And hopefully you're saying no. In water, it is not polar, or it's not soluble, because they're not like each other. One's nonpolar, one's polar. Now, will iodine be soluble in CCl4? Well, iodine's nonpolar, and so is CCl4. So with this one, yes, it will be soluble. They are in terms of their polarity, they're both nonpolar, so they will be able to be dissolved in one another. Okay, let's answer this one. Will sugar, okay, here's sugar. It's polar. Will it be soluble in water? Well, let's look. Water's polar, so yes. Like dissolves like. Will sugar, which is polar, be soluble in CCl4, which is nonpolar? And hopefully you're saying no. So again, this principle of like dissolves like. Let me show you another example that I think we're all familiar with. If you've ever tried to mix oil and water, you will notice if you stir oil and water together, it looks like they're mixing. So if you were to stir this together, it looks like they're mixing. But the moment you stop stirring it, the oil is going to separate from the water. And oil is less dense, and it's nonpolar. Water is polar. So remember that principle, like dissolves like. These are not like each other, so they're not going to be soluble in each other. So this is what it says. Nonpolar molecules will dissolve in nonpolar solvents. Polar molecules will dissolve in polar solvents. So like dissolves like. And that's why oil and water don't mix. Okay, let's talk for a second about factors that will affect solvation. So factors that will affect how something is dissolved. Solvation occurs when solutes collide with the solvent. So these solid solutes collide with the solvent. We just got done with the Kool-Aid lab. The solute in Kool-Aid is the sugar. The solvent was water. So when something dissolves, it's when the solutes are colliding with the solvent. So the sugar was just colliding with the water. Well, there's three ways to increase the rate of solvation. So let's talk about three ways to increase how fast something is dissolved. Number one, if you agitate it, so agitation, that will help things dissolve faster. Surface area. If you have more surface area, you're going to dissolve it faster. And number three, the temperature has a big influence on how fast something will dissolve. So we're going to talk about these three things in more detail. Agitation, surface area, and temperature. Let's go to agitation first. Agitation is the stirring or the shaking of the solution. So whenever you stir it, so like in the Kool-Aid lab, you got a spoon and you stir the sugar and the water together, you're agitating it. Well, agitation increases. It increases the solute and solvent collisions. So you're causing them to collide more, which is necessary in order for something to dissolve. So here's a question for you. It's pretty obvious. But down here you have a sugar cube in cup A, and in cup B you have another sugar cube, same size. Which one will dissolve first? Which one will be dissolved fastest? And hopefully you're saying the sugar cube in A, because he's stirring it, the water is going to collide with the sugar, the solute, and these solvent collisions will happen faster, and so it dissolves faster. Okay, so yeah, the example was stirring helps dissolve the sugar powder when making Kool-Aid. Okay. So agitation, it just is one way to increase how fast something dissolves. Okay, now let's go to the second one, which was surface area. Breaking the solute into small pieces increases the surface area. So when we take the solute and we break it up and we kind of crush it up into small pieces, we're increasing the surface area. The greater the surface area, the greater surface area allows more collisions. So now there's more surface for your solute to be colliding with the solvent. And that's what helps it dissolve faster. So if we look down here, it says which will dissolve faster in 1 liter of water? Would it be a sugar cube, granulated sugar, or powdered sugar? So if you were to put all of these in a liter of water, 3 separate liters of water, which one would dissolve fastest? And I hope that you're saying right now that the powdered sugar will dissolve fastest. It will. But why? And the reason, it goes back to surface area. There's just more surface that's going to be able to touch the water, that it's going to dissolve faster. Now, yes, the sugar cube will dissolve if you leave it in there long enough. But if you look at the sugar cube, on the inside, it's not going to be touching the solvent. It's not going to be touching the water until the outside dissolves. So that's why in chemistry, when you crush something up, it will dissolve a lot faster. A lot more of it's touching the water. So we increase the surface area, increases the rate at which it dissolves. Okay, last one. The last factor that increases the rate at which something dissolves is temperature. And here's the deal. As temperature increases, so does the rate of solvation. So if we have a hotter solution, a solution that's at a higher temperature, it will be able to dissolve the solute faster. So increased temperature of the solution also will allow for more solutes to be dissolved in the solution. So if you have a solute, say you're putting sugar in water, in really cold water, and you're stirring it around and you just can't get it to dissolve. Well, one thing you could do is increase the temperature. It will dissolve it, and then you will even be able to put more sugar in there at a higher temperature, and it will also dissolve it. Okay, an example. Sugar will dissolve much faster in hot water than it will in cold water. And I want you to think about why. Think about the speed of the molecules. As you heat them up, the molecules will move faster. They just have more energy. And so there's more collisions. You're allowing them to collide more. The solvent, the water, is going to collide more with the solute because it's at a higher temperature, and you're going to see more collisions. More collisions, you're going to dissolve it faster. So, okay, I'm going to finish this lesson with this slide here. This is a graph, and it's a good idea to always look at what the graph is reporting. So on this y-axis, we're measuring solubility. It's grams of solute per 100 grams of water. On the x-axis, it's reporting temperature. And I want you to think about the general trend of this graph. As temperature increases, what happens to the solubility? How much is being able to be dissolved? The general trend, almost all of them, kind of go up. So as temperature increases, you can dissolve more solute per equal amount of water. So as temperature goes up, solubility increases. It also depends on the substance. Okay, for each substance, this is different. There's one on here that actually will go down, but that's kind of an anomaly. Most substances, when you increase the temperature, you will increase the amount of its solubility, so you can dissolve more in a given amount of solvent. Okay, that is it for this lesson. Okay, I hope now that you have a better understanding of solubility, and that when you hear soluble, you just are thinking that it's able to be dissolved. I hope now that you have a better understanding of how to increase the rate at which something dissolves. There's 3 ways. Agitate it, which means to stir or shake it. Increase the surface area so you can break it into smaller pieces. That will help it dissolve faster. And also temperature. If you increase the temperature, you're going to increase the rate at which something is dissolved. All right, in terms of worksheets, there's not really a worksheet that goes with this lesson in the student workbook, but it was important to cover those topics, and so hopefully you have a better understanding of solubility and how to increase the rate at which something dissolves.